Hello everybody, and once again welcome. Uh, Today we are going to do some numericals based on electrical field, and this is for the Ibdp curriculum, and the chapter name is electrostatic forces. Electrostatic and magnetic fields. Okay, it's from this particular chapter. So in this particular video we are going to do a numerical based on electrostatic field, the strength of the electrostatic field. Okay, now before we go to the numerical, let me just give you a brief about the concept. So this electric field strength or the electrostatic field strength, it is also known as the intensity of the electric field. Okay, so whether you call it intensity of the electric field or you call it electricity field strength or electric field strength, both means one and the same. It is denoted by capital E with the arrow mark on top of it. That means it indicates that it is a vector quantity. So your electrostatic field strength E is a vector quantity. It means it has a magnitude as well as direction. Okay, now we have studied that in an electrostatic field there is always an electrostatic force acting, and that is denoted by Fe, which is also a vector. It's a force, so it is a vector, and it is given by this formula K multiplied by Q multiplied by Q naught divided by R square, where Q naught is the test charge. Okay, and Q is the charge due to which the field is created. Okay, so this is the formula for the electrostatic force. Now this electric field strength E, okay, is given by this formula. E is equal to K times Q divided by R square. So Q is the charge due to which the electric field is created. Okay, R is the distance, okay, of that particular point where you want to measure the electric intensity from the charge. Okay, so suppose you have a charge Q over here and you have a point P over here, and the distance between these two is say R. Then the electric field strength at P, denoted by EP, you can say, is given by this formula K times the charge which is responsible for creating the field, that is Q, divided by the distance square, the distance between the charge and the point. Okay, so this is the formula for the electric field strength at a point, at a distance of R from the charge Q. Okay, so this particular formula E equal to KQ upon R square is something that we are going to use in the numericals, which are based on this electrical field strength or electric field strength. Okay, now what is the definition of this? The definition of intensity of electric field due to a charge Q at a distance R from it is defined as the electrostatic force acting on that particular point per unit charge on that particular of that particular test charge. Okay, so this is the definition. From the definition we can say that electrostatic field strength E is the force acting, so you can say Fe, this is the force acting per unit charge. Okay, so per unit charge means divided by Q0, isn't it? And force acting is given by this formula. I told you Fe is given by this formula K times Q naught divided by R square divided by Q naught. You will get a Q naught over here, so Q naught gets cut. So ultimately your E formula, that is electrostatic field strength formula, becomes K times Q divided by R square. So I have taught you the derivation also of this particular formula. Okay, can you see this formula? One and the same, and this is the definition, right? Now based on this particular formula we are going to solve one numerical for today's session, and that numerical is this one. this particular numerical. Okay, numerical number 1. We are going to solve some 3-4 numericals based on this or more also. So this is the first one. Now what is the numerical saying? An oxygen nucleus carries plus 8e charge. Calculate the electric field strength at a distance of 0.68 nm means nanometer from the nucleus. Now he is talking about the oxygen nucleus. When he is talking about the oxygen nucleus, what he means to say is there is only the nucleus of oxygen, and you know oxygen of a or any nucleus of any atom contains only protons and neutrons. Protons are positively charged particles and neutrons are neutral particles. So basically any nucleus is nothing but a positively charged quantity, okay, or positively charged, we can say a positively charged particle, okay, a huge particle but a positively charged, because nucleus contains only protons and neutrons, okay. So he is saying that oxygen nucleus and it is carrying plus 8e. So what is this charge? Plus Q is equal to 8e. Now E is the charge on one electron. So 8 times charge on one electron is 1.6 into 10 raised to minus 19 coulomb. Now electron has negative charge, but we are taking only the magnitude of that electron. Okay, so it will be 1.6 into 10 raised to minus 19 coulomb. So this is the total charge on the nucleus, right? So suppose you have a nucleus over here, oxygen nucleus. It is having plus 8e charge. That works out to 8 into 1.6 into 10 raised to minus 19 coulomb, right? So this is the charge. And he has asked you to calculate the electric field strength. So he has asked you to find out E, okay, at a distance of 0.68 nanometer from the nucleus. So from this nucleus, the distance of this particular charge, this particular point, okay, this point is suppose say P, right? So we are trying to find out electric field strength at P, EP, right? So this particular point P is at a distance of R, which is 0.68 nanometer. When you say 0.68 nanometer, okay, it means 0.68 nano means 10 raised to minus 9, okay, meter. So 0.68 nanometer is actually 0.68 into 10 raised to minus 9 meter. Nano means 10 raised to minus 9, okay. So with this as the background, let us try to find out the electric field strength E, okay, at the point P. So we want to find out EP. Okay, now remember it's a vector quantity, so you will have to find out the magnitude as well as the direction. Okay. Now what is the charge on one electron? Charge on one electron, the magnitude I am talking about. It is a negative charge, but we are not considering the negative or positive sign. What is the charge on one electron? It is 1.6 into 10 raised to minus 19 coulomb. So 8E will have total charge. How much? It will be 8 multiplied by 1.6 into 10 raised to minus 19. And that if you work out 8 into 1.6 works out to 12.8 into 10 raised to minus 19. And this 12.8 can be written as 1.28, and this 10 raised to minus 19 will become 10 raised to minus 18. So 1.28 into 10 raised to minus 18 coulomb will be the charge. Now this, if I round it up, 1.28 can be written as 1.3. So ultimately your charge 8E is equivalent to 1.3 into 10 raised to minus 18 coulomb. So this is the charge, okay, due to which the field is created, and with respect to this charge at the point P, we have to find out the electrostatic field strength, that is EP, right? So the formula for EP is K times Q divided by R square. So K value, now since this is in vacuum, K you will have to take as 9 into 10 raised to 9. This is the value of K for vacuum, okay. So K times Q divided by R square will be 9 into 10 raised to 9 into Q value we have just found out over here. It is 1.3 into 10 raised to minus 18, right? This is the total charge. So into 1.3 into 10 raised to minus 18 divided by the R square. R is how much? It is 0.068 into 10 raised to minus 9 meter. You have to take in meters, okay? So here I have written 0.68 into 10 raised to minus 9 the whole square. Okay. So here the care that you have to take is the charge must be in coulombs and the distance must be in meters. And that is how you are following the SI system. Okay. So I have converted the charge into coulombs and the distance into meters, and then I am doing the calculation. Now when you work out this, okay, you will get 11.7. See, 9 into 1.3 is 11.7, right? 9 into 1.3 is 11.7. 10 raised to 9 into 10 raised to minus 18 will be 10 raised to minus 9. So you get this numerator 11.7 into 10 raised to minus 9. In the denominator, you have 0.68 into 10 raised to minus 9 the whole square. So this will be nothing but 0.68 square, which is 6.8. And 10 raised to minus 19 square will be 10 raised to minus 18. So, okay, no. This 0.68, you know, into 10 raised to minus 9. First, I will do what? I will convert this into 6.8. Okay, so to make it 6.8, I will multiply by 10. So I'll have to also divide by 10. So divided by 10 will be upon 10 over here. So this will be minus 9, minus 1. So 10 raised to minus 10. Okay. So this particular quantity 0.68 into 10 raised to minus 9 can be written as 6.8 into 10 raised to minus 10 and the whole square. Okay. Now what I will do, 11.7 divided by 6.8 the square I will do, multiplied by the remaining thing will be in the terms of 10 raised to something. So this will be 10 raised to minus 9 on the numerator, and in the denominator it will be 10 raised to minus 10 the whole square is 10 raised to minus 20. That minus 20 if I take up in the numerator, it will become plus 20. So 10 raised to minus 9 plus 20 is the factor that I will get in 10 raised to something. Okay. And on the left hand side I will get 11.7 upon 6.8 square. This is that. Now on the calculator, when I do 11.7 upon 6.8 square, I get the answer as 0.2530. Okay. And this part is 10 raised to minus 9 plus 20. That works out to 10 raised to 11. So this is my answer, 0.2530 into 10 raised to 11. Now this again, I will bring it in the scientific notation form. So it will be 2.5 into 10 raised to 10. To bring it, to make it 2.5, I will multiply by 10. So it will become 2.5. But if I multiply by 10, I will also have to divide by 10. So that divided by 10 I will use here, and I will make it 10 raised to 11 minus 10 minus 1. That is 10 raised to 10. So this ultimately becomes 2.5 into 10 raised to 10. And the unit for this particular electric field strength is Newton per Coulomb. So this is your answer. Okay. So the answer for this today's numerical is the electrical field at the point P, which is at a distance of how much? 0.68 nanometer. So this was the charge. Okay. The charge was how much? Plus charge. It was 8 times 1.6 into 10 raised to minus 19. From this charge at a distance of 0.68 nanometer, there was a point P, and at this point we found out the electric field strength to be how much? This much. This is the answer, 2.5 into 10 raised to 10 Newton per Coulomb. This is the magnitude of the electric field strength. As I told you, electric field strength is a vector quantity. This is a vector quantity. So you should know what is the direction as well. Okay, because it is a vector quantity. This is the magnitude, 2.5 into 10 raised to 10 Newton per Coulomb is the magnitude. What will be the direction? Now direction will be, now this is a positive charge. Okay, so any positive charge will always have the electric field lines, okay, going outwards away from the charge. Okay, so at this point P, the electric field will be along this particular line. Okay, so it will be going this way. So your EP, the direction of your EP is away from the charge Q. Okay, along QP. Okay, along the line QP. So it will be going away from the charge. Okay, that is the direction. Is that understood? So that was numerical number 1 based on the electric field strength, and in the next video we'll be doing more and more numericals based on this electric field strength. Okay, that's all for today. See you in the next video very soon. Bye.